guys, today we are going to deal with and address something completely new for my Math 2 students. We are going to tackle some questions that look like this, or give you answers like this, from a graphical perspective. If I were to go in and graph this guy in Desmos, y equals x squared plus 16, and I ask you to solve this quadratic equation, poof, it disappears right off the face of Desmos. And of course, if I do a little zooming out scroll, I realize that this guy doesn't even cross the x-axis. And as we've been talking about, if we solve this thing graphically, I would say it has no real solution. Let's take a look at what that looks like algebraically. In our last video, we showed you how to solve this using the roots method, which would probably be how I would approach this if I were doing it by hand. So I would subtract 16 from both sides, and I get x squared is equal to a negative 16. And if you're not careful, you'll just hurry up and take the square root of that, and you tell me that it's plus or minus 4. But we realize that I actually can't take the square root of a negative 16. There are several ways that you can look at that. First and foremost is that's outside of the domain of the square root function. If you look at the domain of a radical, which we will talk about a little bit more in depth later, but the domain of a radical says that all these values that are inside here of this radicand, these values have to be larger than 0. And the other thing is, when you begin to think about it, when you talk about a square root, you're talking about, what number can I multiply by itself and get that number? Well, the only way you can multiply two numbers and get a negative is if one of them is a negative and one of them is a positive. So, negative 4 times negative 4 is positive 16. And 4 times 4 is 16. So, there's no way that you can multiply the same thing by itself and get a negative 16. So, this is where we begin saying that there are no real solutions, and I think that's the key to today's lesson. Is it's not so much that we're talking about the real solutions. We want to talk about the unreal solutions and what we like to call the imaginary or complex solutions. So that's what today's lesson is going to be about. In today's lesson, we're actually going to do the following two things. We're going to talk about these imaginary numbers or these complex numbers. And again, notice that this guy right here says that it is part 1. There's going to be 2 parts to this video series. The first part is we're just going to simply address what is an imaginary number, exactly what it is, because I want you to understand that first and foremost. It's kind of like today you get the rest of the story. And, as you progress through your high school career in mathematics, we've talked about how, these things build and they grow upon each other. So today you're going to get the rest of the picture, the rest of the numbers, if you will. And then not only that, the first step in that is dealing with and simplifying various powers of I. Not just I to the first power, or I squared. But, before we really talk about that, we really need to understand what is an imaginary number. So that's going to be the first part today. And then after we do that, we're going to learn how to deal with various powers of I. The second video in this series, and there are only going to be 2 that deal with imaginary numbers, is literally dealing with operations. Adding, subtracting, multiplying, and dividing, and how to do those things with imaginary numbers. That said, let's get into this, starting first with imaginary numbers, what they are, complex numbers, and I'll differentiate between what an imaginary versus what a complex number is, and how that fits into the real number system. So here we go. This is a schematic that I have been using over the years, so let's talk about numbers first. For the better part of your mathematical career, from kindergarten all the way up to this point in your life, you have lived on this left side of this model, from the real number system where you've lived right here. That's all you've ever known. These are your real numbers. And, literally that's where you've been living your entire life. Real numbers can be broken down into the rational numbers and the irrational numbers. Remember, rational numbers are simply numbers that can be written as a fraction. These irrational numbers cannot be written as a fraction. You're talking about numbers like the square root of 2, for example, or pi, 3.14159. It just keeps on going. It's a beautiful thing. These numbers cannot be written as fractions. The rational numbers can be broken down into the integers. A subset of the integers are the whole numbers, and of course the lowest classification we generally talk about are the natural or the counting numbers. You know, those numbers start with 1 and 2 and 3 and so on. But then you notice in the schematic that there's an entire other section over here, imaginary numbers, but even above that you have sort of the hierarchy of it all. You have the complex numbers. And that's what I want to talk about. All complex numbers have a standard way of being written. They are written as a plus bi. That's how you would write a complex number. And when you write that complex number, it actually has two parts. The a, right here, this represents the real part, and the bi is the imaginary part of that number. So all the numbers, everything that is up here, actually can be written that way, whether the number is strictly real or strictly imaginary. The thing that I like to tell people is, all the real numbers over here, if everything is complex, that's the hierarchy. So all your real numbers, if it's just classified as a real number, that means that b value is equal to 0. And of course, that's always going to hold true. Anything times 0 is 0, so you would just be left with the a portion, which is just strictly the real portion. But complex numbers have a real part and an imaginary part. So we're going to talk about that bi part. Specifically, we need to talk about a at b and then I separately. A and b are just numerical values. Those are real numbers. But the I part, that is what makes an imaginary number. What exactly is I, this mysterious letter? And it's not the thing that we all have in our head, but it's the letter I. In mathematics, I represents the square root of a -1. That is the imaginary unit. Now, I need to stop and just take a pause for a second and make you realize that this is not a comprehensive video on the understanding of imaginary and complex numbers. There is a vast wealth of information out there above and beyond this, and fields of mathematics that use these imaginary numbers all of the time, that you can take whole classes in colleges on it and things like that. It is an awesome subject. I'm just going to be dealing with and addressing what you guys need to know for Math 2 through pre-calculus, really, and how it pertains to you. So again, it's just sort of an introduction to that. So I is equal to the square root of a -1, which kind of takes us back to our understanding of the original problem. We see that we had the square root of a -16. So we're going to use that information as it pertains later to actually help us understand how to deal with imaginary or complex answers. So what I want to walk you through just for a minute is a couple of different, or actually 4 total different powers of I. Now, just like everything else, you could take I here, interestingly enough, and we could let me add another slide in here real quick. We could take this value of I, if that's equal to the square root of -1. And then what we would do then at that point, again, that's what is known as the imaginary unit. That one little number is what makes an imaginary number an imaginary number. If I say 5i, I'm talking about 5 times the square root of -1. If I say 3i, I'll write that 5i is equal to 5 times the square root of -1. If I were to say 3i, that's actually 3 times the square root of -1. And that one letter, that I, if you will, that I is what is going to make this guy an imaginary value. Just that little guy right there. That's what makes it imaginary. The 5 is still a real number. The 3 is still a real number, but it's the I. The I is what makes it imaginary. So let's move on. As I said, there's, one of the things that we need to learn to deal with first and foremost are the varying powers of I. So let's take a look at I, and this time I want to square it. So if I just look above, I is equal to the square root of -1. So then what would I squared be? Well, let's just figure that out. We would square the square root of -1. And of course, our understanding of radicals for Math 1, we understand that the square root and the square, they just cancel each other out. So I squared is actually equal to -1. So interestingly enough, and this is going to become extremely important later, especially when you get over into Math 3, if I square the I, it goes from being imaginary back to being real. I cubed, we'll take a look at it. Using our rules of exponents, I can break that apart to be the following. I times I squared. And so what I've done here is I've broken this I cubed, a new thing, into two familiar ones, I and I squared. I is the square root of -1. I squared is -1. So that's actually just equal to -I, or negative square root of -1. However I would like to look at that. Lastly, it would be I to the 4th power. Let's look at that guy. I to the 4th power. I to the 4th power, using our rules of exponents, I can break apart to be I squared times I squared. And I'm doing that because I'm taking things back to their real. You know, real numbers are still something that we're more comfortable with. So taking this back to its real counterparts, I squared is -1 times -1, which is just 1. So when you take a look at all the different things that are up here, you can begin to see the varying things in the relationships. I is the square root of -1. I squared is equal to -1. I cubed is equal to -I, or again, the square root of -1. And then finally, back to I to the 4th power, that's just equal to 1. Now, when I said we were going to learn how to deal with powers of I, in a minute we're going to talk about how to deal with something crazy like, what is I to the 632nd power? Something insane like that. But first, a little bit of, let's look at some patterns. Let's kind of see if we can draw out something interesting about that whole scenario. So, dealing with the powers of I. So I'm going to write all that stuff down again that we just spoke about with the different powers of I. So again, one more time. I is the square root of -1. Condense it a little bit and reduce the amount of work we had. I to the 2nd power is -1. I cubed is -I. I to the 4th is 1. Now watch what begins to happen. I to the 5th power. Well, again, using our properties of exponents, that is I to the 4th times I. I to the 4th, we know from what we just talked about is I to the 4th, and this is going to be the one that we deal with the most because everybody likes the number 1. The number 1 is like everybody's favorite number next to 0. I to the 4th is just 1. So this I to the 5th is like saying 1 times I. So that's just I, which is the square root of -1. Watch what happens with I to the 6th. Again, using our friend 1, that's I to the 4th times I squared. And remember, when I'm saying the properties or the rules of exponents, remember when you're multiplying bases together, you add the exponents. That's why I'm allowed to separate those that way. And again, I to the 4th is 1. So I to the 6th is the same thing as I squared. And I hope you will begin to see a pattern now. I to the 7th is the same thing as I to the 4th times I cubed, which again is just I cubed. And then I to the 8th is literally I to the 4th times I to the 4th, which makes it the same thing as just the number 1. So what you see there, you see the repetitive nature that you have going with these values. Let me change color so I can point this out. So you see that every 4, it repeats. It just begins to repeat. The pattern will continue to repeat over and over and over again by a factor of 4. So then when I go up here and I say, okay, well, neat, what about I to the 9th? Well, again, when you start thinking about I to the 4th power, and this is what I begin to examine this just a little bit closer. I look at the 9, right? How many times will 4 go into 9? Well, 4 will go into 9 2 times. That means I have 2 of those I to the 4s. And I get a remainder of 1. So that means I to the 9th is the same thing as I to the first power, which is just I. And I can continue that pattern over and over and over again, so that we can still deal with larger and larger exponents or powers of I, all the way to I to the 12th, which is the same as I to the 4th. And again, the reason why, there isn't a remainder, so it goes into an even. All right? So then that allows us to be able to answer some more difficult questions. Now, I would be amiss if I didn't tell you that you can take your TI-83 and your TI-84, and you actually can go under mode and put this thing under the TI. Again, I'll just write this down real quick. The TI-83 and the 84, you can go under mode, and you can switch it from real to a+bi. And then when you do that, your TI-83 or TI-84 will actually be able to work problems in imaginary mode. So, I can type in I to the 12th power. It would tell me it was 1, and so on and so forth. So that's a really neat thing about the 83 or 84. But let's do some of these problems dealing with 4. We want to, because again, I to the 4th is 1. We want to see, as I deal with bigger and bigger powers of I, what that would look like. So let's call this example 2. Change color so we can see that. Example number 2. Simplify the following. So let's look at I to the 77th power. Man, that's a big number. But again, remember, I to the 4th is just equal to 1. So if I can figure out how many I to the 4th are in 77, man, I can make this thing really simple. So what I'll do is just, if I've got a calculator, fine. But sometimes just doing some old school long division, there's nothing wrong with that. So 4 to the 77th power. You ask anybody that I've ever sat in the classroom with, they'll tell you I love my technology. But sometimes just some old school long division written off to the side of some scratch work is just gold. So, 4 will go into 7 one time. You're left with 37. All right. So how many, 4 times what gets to be close to 37? Of course, that's 9. All right. So 4 times 19, there we go. Or excuse me, 4 times 9 is 36. And I've got a remainder of 1. So what that tells me is that this thing is actually, and again, this is what's so epic about this. We'll write this out in extended form. That's actually I to the 4th. And I got 19 of those guys, right? I to the 4th to the 19th power times my remainder. This is using the division algorithm. And if, it takes me into Math 3 when we start talking about dividing polynomials a little bit more. But using that division algorithm, I realize that that's going to be I to the 1st power. So that's how that thing breaks down. So again, if you need to check that, 4 times 19 gives me 76, plus the additional 1 gives me that 77th power. So there are 19 I to the 4th there, but really and truly what that means is all of that is just the number 1. Every bit of that, that's just the number 1. So then I've got 1 times I to the 1st power, so it's just equal to I. And that's the beauty of doing that long division off to the side. And of course, I love my technology, but it's not going to tell you what the remainder is. And that's the crucial component, is knowing that remainder. So let's talk about that for a minute. What do I do? Okay, well, listen, when you're dividing these numbers by 4, you're really only going to get but 4 different remainders. So let me make you a little chart here. Do this real nice and neat. So after you do the division, and again, you're only going to get 1 of 4 possible remainders because I'm dividing by 4. technically you're only going to get one of three remainders. The other one will be a remainder of 0. So if my remainder is a 1, that means my power of I is I to the first power. If my remainder is 2, that means I've got I squared. If my remainder is 3, that means that it can reduce to I cubed. And if my remainder is 0, that means it's I to the fourth, which just means it's our lucky number 1. All right, so that's how that can work out for you. But again, this is your remainders from doing long division. So taking that into consideration as we go forward and we do some of these problems, that's going to help us understand, hey, do my long division with that exponent, divide it by 4 to see how many of those 1s go into it, and then we can get an answer. Let's do another one. And, you can get crazy with these things. How about this guy? Let's increase our numbers just a little bit. Let's look at I to the 103rd power. Now this one's not too bad because, you see the 100, and of course that's evenly divisible. So if I did the long division, what I would end up seeing is that that'll go into that 25 times with a remainder of 3. So, and again, if you want to see that off to the side, 4 won't go into 1, so we look to the 10. How many times will 4 go into 10? Of course, it's twice. 4 times 5 gives me 20. And again, I've got the remainder of 3. So that means, using my little chart that I had over there, that means this guy's the same thing as I cubed, which is, of course, negative I, or the opposite of the square root of negative 1. However you want to put it, any one of those answers is sufficient. But again, you can get just as crazy with this as you absolutely want. I mean, I have seen some insane things like, how about I to the 237th power? I to the 237th power. So again, all you got to do is take that. 4, how many times will it go into 237? So you work out all the math, and we're just going to get straight to it. You do that, you're going to get 59, a remainder of 1. So there again, that right there, it is the same thing as I to the first power, which is just I. That is it for this lesson. If you have any questions or comments, please be sure to leave them in the comment section below. And again, this was part 1 of 2. When we come back to our next video series, we're going to actually talk about how to do operations, add these complex numbers, subtract these complex numbers, and then multiply and divide them together. I hope this helps. We'll talk to you guys soon. Have a great and wonderful day.